Hello, Math 20-1. We're going to continue our studies with geometric sequences. And you've got some former Math 20-1s that are watching the show just to see if we get this right. Right, Cole? All right. So one of the things about geometric sequences is they aren't going to follow the same pattern as arithmetic. They're different. There are many patterns. We looked at Fibonacci's that follow different types of sequences, and we need to discover this new one. So one of the examples I'll just play is an example of a spider spinning a web. So as you can see, this sequence that is being spun by this spider should form an arithmetic sequence. The links of silk between the radii for each section of the spiral produces a geometric sequence. And we may not be clear on what that exactly is right now, but 8, 12, 18, 27, clearly that's a sequence of numbers, and that follows a geometric sequence. I'll give you another example that may be closer to your heart, but you yourself are the product of a geometric sequence. You started on one evening or night, or we're not sure where, but you started as one cell. And there's some biological things that happened, and that one cell became two. And those two cells became four, and those four cells became eight as a result of cell division. And along came you, and this is an example of exponential growth of cell division. And it obviously is quite a miracle when it all comes together to create a human being, right? But that's an example of exponential growth, which is a geometric sequence. We continue on and go, okay, well, what exactly is it that makes a sequence geometric? And if you look at these patterns, clearly when we think about arithmetic, they don't have a common difference. So what is it that defines a geometric sequence? Well, let's find out. All right, well, let's look more into examples that are and are not geometric. So one example would be 2, 10, 50. This is an example of a geometric sequence. What is not is 10, 15, 20, 25. It might seem familiar, but that's arithmetic. -4, 12, -36, that is geometric, whereas this one is not. This fractional one is a geometric one, but this is not. Where would these sequences go? So now that we've seen some examples, where would each of these go? Ponder that and come back and see. Well, -1, -3, -9 goes here, but this one goes here. So it's time to ponder now, what is it that makes, what's the criteria that makes something geometric and something that not? And it's a good time for you to try and discover it on your own rather than wait for the notes. So give it a go and see whether we can come up with that. And if you can, what would the next term of each of these be? So could you write the next term of each of these? Would that be possible? So for the first one, it'd be 250, and the next one, -324. The next one would be 1 over 2187, and the last one would be -27. Maybe it's 100% clear now, and maybe it's not. So what we'll do on the next slide is we'll look more closely at these patterns and see how we can discover what exactly a geometric pattern is. So back to the spider example with 8 and 12 and so on. What's the relationship between these numbers? Well, if we look closely, the relationship is not arithmetic. We can't subtract these two like we did before, right? If I subtract the two, I get 12 minus 8 equals 4, and I get the next two consecutive ones, 18 minus 12 equals 6, and that's not a common difference. That's not arithmetic. But if we look, what do they share in common? We can see that if I divide them, I get something common, and I get 3/2 or 1.5 for each of them. An ordered list of terms separated by commas in which there is a common ratio between consecutive terms is called geometric. Multiplying any term by the constant called the common ratio will give the next term in the geometric sequence. And just to show you one that might be easier, a little biological one, if we think of 1 and 2 and 4 and 8 and 16, whenever we take any two consecutive terms, 16 divided by 8, or 8 divided by 4, or 4 divided by 2, in every pair of consecutive terms, we end up with a common ratio of r equals 2. Consider the sequence 4, 8, 16. What's the value of term 1? Clearly we can see that term 1 is 4. And what would term 4 be? Well, term 4 would be 32. If you want to determine the value of the common ratio, as we discussed, we simply divide consecutive terms. And if I pick 8 and 4, I would get 2. What strategies could you use to do term 10? And we talked about this earlier in the unit, where common sense can play a really big role in this unit. And if you want to think of it as a frog jumping, your frog jumps by doubling. So think of ways you could do without a formula. Obviously we're going to come up with a formula, but ponder what you might do. Okay. One of you might say, well, if I start with 4 and I have to go from 4, which is term 1, to term 10, so that would be term 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this is term 10, I simply have to jump 1, 2, 3, 4, 5, 6, 7, 8, 9 times. And if we were doing a arithmetic, we would always be adding d, but we're not doing that. In this case, we are multiplying by r, multiplying by r, multiplying by r, multiply by r, multiply by r. So in the end, to get from term 1 to the end, or term 10, you will have to take term 1 and you will multiply by r 9 times. And in this case, we can see that term 1 is 4, and I'm going to multiply by 2 to the 9, which is going to be, if we talk about cell division, a lot of cells, right? What would the graph look like if you graph this? Well, if we graphed it, we can see that this is not going to be the line that Mr. Zotner talked about when he taught you section 1.2, that in an arithmetic graph, we have a consistent, for every term we go up by the same difference. This is exponential in nature, and the terms go up by progressively more and more as it doubles, right? What's the rule for this? Again, we follow that same type of chart and look at the patterns. So if we look at term 1, it's 4. And expressed in terms of the common ratio would be just 4. But term 2 in the sequence would be 8, and that would be 4 times our ratio of 2. So term 1 times r. Term 3 would be 4 times 2 and 2, so that'd be term 1 times 2 r's. And term 4 would be 4 times 3 r's. So term n, a little bit different than the arithmetic sequence, is going to be a frog starting at term 1 and multiplying by the common ratio n minus 1 times. So the general formula for a geometric sequence is term n equals the first term times r to the n minus 1. When we talk about what assumptions can be made, one of the things that we could talk about is that we have to have n as an element of, in this case, natural numbers. That the terms here cannot be negative, and you can't have 1.5 terms. N has to be an element of natural numbers. So we talked about finding term 10. If we use the formula version rather than common sense, we can simply plug into the formula like we did with arithmetic and get term 1 is 4, n equals 10, and r equals 2. Therefore, when we plug in, we get term 10 being. So the second part of this question is to complete the general term for this particular sequence of numbers, just like we did with arithmetic. So in this case, once again, we use our formula, and we define term 1 in r, and we know in this sequence that term 1 is clearly 4. Our common ratio is 2, and n, because it's a general term, is just a variable. We plug that into our formula and we get this as a general term. Now, certain textbooks might simplify this in different ways, but you must not multiply 4 and 2. When you ponder laws of exponents, we cannot multiply two numbers together unless they have the same base. And so we simply can't go 4 times 2. And the question is asking, well, is it okay if I write term n is equal to 4 times 2 is 8 to the n minus 1? And that would be, no, you can't. Don't do that, because clearly that's going to result in something mathematically highly illegal. We cannot multiply those two numbers together. So that's our general term. And if we used it, we could find out the value of any term. To go back to our Spider-Man theme, we have Spider-Man being bitten by a spider and injected with 1 milligram of venom into his body. The venom concentration doubles every hour. Ooh. So we need to make sure we underline the key components to the question and then use that to answer the questions below. Okay. Now, when we start doing practical questions, you have to be aware of what term you're looking for and not just blindly use the formulas. So in this case, write an expression that models the concentration of venom in a spider's body over time. So if we use the TN formula, we clearly know that term 1 was 1 milligram. The common ratio was 2, and as n goes by in time, it's a variable. How many milligrams were in Spider-Man's body 8 hours after being bitten? Now, the key point here is that, does n actually represent hours? Well, n isn't really hours. N is the number of the term. So n as a variable needs to be considered as not necessarily, it's the number of the terms. Now keep that in mind. I want you to try, complete this question, then come back. What value of n should be put there? All right, when you're done and you have an answer, come back and check. Turns out that n needs to be actually 9. And the reason it's 9 is that at time 0, it's 1. And so 8 hours later, you're actually going to be at term 9. So if you just draw a little common sense map and we say, okay, well, what's term 1? Term 1 is now. And as you jump, this is 1 hour later, 2, 3, 4, 5, 6, 7, 8, 9. So this is this is 8 hours later, but it's actually going to be term 9. And so when you start doing common sense questions, you need to be careful that you're actually plugging in the right value for n. Right? Term 9, there would be 256 milligrams of the venom in Spider-Man at the end of that time. Right? Complete the assignment from your formative work, and we will see you in class.